Welcome back to my YouTube channel all about VLSI. From this video, we are going to start with UVM verification of AXI-4 Lite wrapped FIFO. So what is this design? First of all, let us try to understand. Then we can start with different kind of test cases we are going to have and what is the UVM testbench structure and all we are going to learn in this particular series. Now, basically, we are going to have a FIFO. This FIFO, as of now, I'm considering it as an 8 cross 8 FIFO, and if you want, you can keep it as a parameterized FIFO so that you can play with the increasing width or decreasing width, or you can increase the number of locations and all. If you keep it as a parameter, right? Now we have a FIFO which is present with us. Now I'm going to wrap a particular AXI protocol or AXI interface around this particular FIFO so that I can basically send the commands, AXI commands to this, and this will be interpreted by this AXI interface, which was wrapped around this particular FIFO, and that will be forwarded to the FIFO. That is what this particular design is going to do, and that is nothing but my AXI wrapped FIFO. Now, this AXI wrapped FIFO, for this we are going to develop the UVM test bench and we are going to verify using the UVM test bench, right? Now, so what are we verifying? As I've said you, I'm going to have an AXI4 Lite master like my processor. So processor is going to have its own kind of AXI master interface. Through it, it is going to drive some data that will be received by my AXI wrapper. Now, AXI wrapper is going to receive those particular transactions which my master is going to send, and that it is going to forward it to my FIFO. Okay, and FIFO is going to store that particular data into the into its own locations, right? And if you haven't watched the recordings of AXI wrapped FIFO, I recommend you to watch those particular project series where we have discussed in great detail of how exactly we have designed a particular AXI wrapped FIFO. We are going to have three registers. One is TX underscore data, and another is RX underscore data, and another is status register. So if I want to push any data into the FIFO, I need to provide the address corresponding to this particular register TX underscore data. Then only I'm going to push the data into the FIFO. And I'm going to get a slave error whenever I'm trying to push the data, whenever the FIFO is full, then in that particular case, I'm going to get slave error and my byte is going to drop and I will come to know that, okay, the FIFO is full. Now, if I want to push the data, I need to provide the address as hexadecimal 0. And if I want to read the data, I need to provide this particular address, which is equal to 4. But here I'm going to provide the 4, and here I'm going to get the oldest byte into the R data of the AXI. And I'm going to get slave error when I'm trying to read the data from an empty FIFO. In that particular case, I'm going to get slave error. And next is status. Like let's say suppose if I want to know the status of my particular FIFO, like whether it is empty or whether it is equal to full, I'm going to read this particular status register. So bit 0 is going to tell me whether FIFO is empty or not, and bit 1 is going to tell me whether FIFO is full or not. And bit 7 down to 4 is going to tell me what is the exact number of elements which are present in my FIFO code. So this is the register map which is present inside my design, which I'm going to utilize for either writing the data or reading the data, or for getting for basically going for getting the status of my FIFO. Okay. And where TX underscore data is only write only, you cannot read the contents from that particular register. And RX underscore data is only read only, you cannot write the contents into that particular register. And status register is read only, you cannot write anything into that. Now, coming to my UVM environment architecture, I'm going to have a sequencer, driver, design, DUT, and monitor coverage, scoreboard, and reference model. Okay. And we are also going to implement RAL model since in our design we have three registers, right? So that's the reason I'm also going to implement RAL model in my UVM environment. Now, what is the test case strategy? We are going to have basically four categories over here. I've wantedly removed the one category over here. That category we will discuss later. Now, as of now, I'm going to have only four categories. One is protocol baseline. We are going to check whether handshaking is properly working or not for pushing, popping, or for finding out the status and read back. For all these particular things, is the protocol correctly mapping or not? is a protocol correctly working on the AXI protocol. Okay. Next is register map. So whatever the addresses which we are going to have, like let's say suppose if I want to write any particular data, I need to provide the address corresponding to tx underscore data. Or else if I want to read the data, any particular data, I need to provide the rx underscore data address. For example, if this is my design DUT and this is my AXI interface which is present, AXI wrapper which is present. Now, if we are developing the test bench over here, and let's say, suppose if we are going to provide the address as 0, then that means you are going to perform the write operation. That means FIFO write enable will be made to 1 internally if you are providing this particular address. Instead of this address, if you are going to provide 04, which is corresponding to read. Okay. So what is going to happen if the design is going to see this particular address, it will come to know that, okay, user wants to read the data from the FIFO. So it is going to initiate a read operation. So this we should be careful. If we want to perform the write operation, you need to provide, definitely you need to provide this particular address so that internally design is going to perform the write operation into the FIFO. And if you want to read the data from the FIFO, you need to provide this particular address so that design is going to read the data from this particular FIFO. And if you want to know any kind of status, then you need to provide the address hexadecimal 8 so that you are going to come to know the status of the FIFO, whether it is full, whether it is empty, or whether how many entries have been filled or not. If you wanted to know, you definitely need to specify this particular address for our design. For our design, I'm talking about. Okay. So for our design, if I want to write the data into the FIFO, I need to provide the address 0. And if I want to read the data from the FIFO, I need to provide the address 4. And if I want to know the status of the register or status of the FIFO, I need to provide this particular 8. And in the test cases, we are going to check whether this register mapping is correctly happening or not. When we are providing 00, whether our design is successfully pushing the data into the FIFO or not, how are we going to check it out? We are immediately after providing the address 0, that means it's a write operation. Then immediately we are going to provide the address as 4. So that means it will initiate a read operation so that we will come to know whether whatever we have written, whether we are going to able to store it or not. We are going to check by reading it back. Okay. And also we can check in the status register also. We can check whether what is the count of the FIFO, what is the number of entries which has been entered into the FIFO immediately after write operation. That is what we can check whether all the registers which were specified in the design specification are correctly implemented in the coding level or not. This is what we are going to check in the register mapping. And we are also going to wantedly trying to read from read only registers. You can see I should not try to perform any operation, any write operation on the address 4 because it's a read only register. But let's say suppose if I'm going to grant the address as 4 and I'm going to perform a write operation onto this particular address, it should, what it is going to do, that also we are going to check. It should basically give us slave error, whether it is going to provide any slave error or not. We are also going to check. And let's say suppose this particular status register is read only, but let's say suppose if I want to perform the write operation onto this particular address, then what is going to happen? That is what we are also going to check in our test bench. Next is concurrency and stress. We are going to provide randomized back-to-back and simultaneous AW and AR traffic, and we are going to check what is happening over there. And also we are going to provide mid-transaction reset and clean recovery. So that what is going to happen? Let's say suppose if we are working and in the middle, if we are going to apply the reset signal, then what is going to happen? These are the different kind of test cases which we are going to have. Yeah, that is what I was saying about. These are the different test cases where I'm going to have single push pop or status read back and full FIFO to full or drain to empty and different kind of test cases which we are going to have over here. And this and all we are going to implement in our particular project. And we are also going to have the coverage and assertions which we are going to have, where I'm going to have functional coverage as well as SV assertions. And if we are going to get 100% coverage as well as all the particular test cases are getting successfully implemented, then we are going to come to know whether our particular design is completely working on. So this is what I'm trying to build in this particular project series, where we are going to build the UVM test bench of this particular design. And I'm not going to discuss in great detail about what exactly which is present inside this FIFO, what is the core logic which is present inside this FIFO. As a verification design engineer, this is what the specifications we are going to have, and using the specifications only, we are going to develop our test bench and we are going to check it out. Okay. Yes. So that's about this particular session. Hope you like this particular video. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.